The dorsal stream and ventral stream emanate from a common origin in the visual cortex. Various researchers had put forth similar concepts in the past. The inspiration for this work can be attributed to studies on blind sight by Weisskranz, as well as previous investigations in neuroscientific vision research. The notion of two visual systems for localization and identification was initially suggested by Schneider in 1969. Engel in 1973 observed two distinct visual systems in frogs. Building on this foundation, Ettlinger reviewed neuropsychological evidence supporting a differentiation in 1990. Furthermore, Trevarthen delineated two separate mechanisms of vision in monkeys as far back as 1968. Ungerleider and Mishkin in 1982 differentiated the dorsal and ventral streams, responsible for processing spatial and visual features, respectively, through lesion studies on monkeys, introducing the original where versus what distinction. Despite being surpassed by the model of Milner and Goodale, this distinction continues to carry weight. A significant contributor to this model has been the experimental exploration of the abilities of visual agnostic patient DF. Goodale and colleagues presented the pioneering and highly influential report in 1991, which continues to be a subject of research even 2 decades later. Criticism has arisen regarding the model's heavy reliance on data from a single case study. Goodale and Milner compiled a variety of evidence from different fields to support their model. They proposed that the ventral stream processes visual input to create a detailed map of the world for cognitive tasks, while the dorsal stream transforms visual information to aid in motor planning. The model suggests that visual perception encodes spatial properties like size and location in relation to other objects, utilizing relative metrics and scene-based frames of reference. When it comes to action planning, absolute metrics using egocentric frames of reference define the actual properties of objects relative to the observer. The integration of these different frames of reference helps in reconciling discrepancies in visual illusions when grasping objects against complex backgrounds. Norman also presented a dual-process model of vision, outlining 8 key distinctions between the two systems. The ventral system handles recognition and identification tasks, focusing on details and long-term memory, while the dorsal system is geared towards visually guided behavior, prioritizing motion sensitivity and short-term memory. The two systems function at different speeds, with the ventral system typically slower due to its detail-oriented processing, and the dorsal system faster to aid in real-time actions. Furthermore, the ventral system operates in an allocentric frame of reference, focusing on the object itself, while the dorsal system uses an egocentric frame of reference, centered on the viewer. The dorsal stream, also known as the Howe pathway, is responsible for spatial awareness and guiding actions. It processes information related to spatial properties and object manipulation, connecting the visual cortex to the posterior parietal cortex. Patients like patient DF have shed light on the dorsal stream's role in constructing representations for object manipulation, leading to its nickname, change from the where pathway. The dorsal stream works in tandem with the ventral stream, which is dubbed the what stream, responsible for object recognition and form representation. The ventral stream is intricately connected to areas of the brain associated with memory, emotions, and motion processing. Visual information is processed through various areas in sequence, with each area handling different aspects of visual perception such as color, shape, and integration of stimuli into a holistic image. Damage to the dorsal stream can lead to spatial disorders like simultanagnosia, optic ataxia, hemispatial neglect, achinotopsia, and apraxia. On the other hand, damage to the ventral stream can result in the inability to recognize faces or interpret facial expressions, highlighting the crucial role it plays in object recognition and significance judgment in visual processing. The auditory ventral pathway in Hickok and Peppel's dual pathway model plays a crucial role in processing linguistic information, such as the phrase, "my cat." Phonemes are initially processed into syllables and environmental sounds before converging with the visual ventral stream at the middle temporal gyrus and temporal pole to form audio-visual concepts. On the other hand, the auditory dorsal pathway is responsible for mapping auditory sensory representations onto articulatory motor representations, essential for speech production. This pathway starts at the posterior superior temporal gyrus and sulcus, moving towards the temporal parietal boundary near the Sylvian fissure. In contrast to the ventral stream, the auditory information for repeating phrases like, "What is your name?" enters the dorsal pathway through the posterior superior temporal gyrus. This information then progresses to the sensory-motor interface at the temporal parietal boundary, specifically at the SPT region. Critics of Hickok and Peppel's model have raised concerns about the oversimplification of the dual pathway theory. Recent research challenges the strict separation of visual functions into two streams, emphasizing the interplay between perception and action. Neuropsychological studies have questioned the independence of the dorsal and ventral streams, suggesting a more integrated approach to understanding visual processing. Goodale and Milner propose a perspective where the dorsal stream operates under the guidance of executive functions informed by ventral stream processing, highlighting the dynamic interactions within the visual pathways. Researchers like Robert McIntosh and Thomas Schenk suggest viewing the model not as a rigid hypothesis, but as a heuristic guide for further exploration, advocating for a deeper understanding of how visual brain areas form functional networks in various tasks.